In this video, I'm going to explain you about the Taylor's theorem in Lagrange form of remainder. First of all, let us look at the statement of Taylor's theorem. So first of all, we are taking a function fx which satisfies this condition. So first of all, f of n minus 1 x should be continuous in the closed interval, and f and x should exist in the open interval. Then there exists at least one number theta such that f of a plus h equal to f a plus h f dash a plus h squared by 2 factorial f double dash a plus dot 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 h n minus 1 by n minus 1 factorial f n minus 1 a plus h n by n factorial f n a plus theta h. So this is your statement where 0 is less than theta is less than 1. So this is the statement of Taylor's theorem. So in this theorem, it is given that f of n minus 1 is continuous in the closed interval. So that means that all the all the derivatives below of the order of n minus 1 will be continuous. Okay, and also they have given, it has also given that fnx exists, means fnx is differentiable in the open interval. So after that, if this two condition is satisfied, then we get this equation should be true. We want to prove that this equation is true. So using the condition 1, since fn n minus 1 x is continuous in the closed interval a plus a comma a plus h, so it will be, so all the um means all the function of smaller order derivatives less than n minus 1 or equal to n minus 1 should be continuous. So since fn minus 1 x is continuous in this interval a to a plus h, so all the smallest will be continuous. So that's why we have here fx, f dash x, f double dash x, fn minus 2 x, and fn minus 1 x is continuous in the closed interval a to a plus h. So in order to prove this theorem, we'll consider one function. So we are considering this function phi x. So this is your phi x is equal to f of x plus a plus h minus x, f dash x plus a plus h minus x square, x whole thing squared 2 factorial f double dash x plus dot 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 plus a plus h minus x to the power n minus 1 by n minus 1 factorial f of n minus 1 x plus a plus h minus x to the power n factorial a. So we are choosing this a in one condition. That condition we are taking as phi of a should be equal to phi of a plus h. So if you put this value here, so in place of x, if I substitute the value here a, so we get here just everywhere wherever x is there, you try to substitute a. So if you substitute a, we get nothing but this, which is equal to, we have taken here phi of a plus h. So in place of x, you substitute here a plus h. Everywhere wherever x is there, you substitute here a plus h. So if you substitute a plus h here, we are getting this condition. We are getting like this. So we can see that a plus h minus a plus h here also, so this part also will be 0, here also will be 0. All these things will be 0. Only we are left with f of a plus h. And here a and minus a will be cancelled, a and minus a will be cancelled, here also same way. So we are getting here f of a plus h f dash a plus h squared by 2 factorial f double dash a plus dot 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 h n minus 1 by n minus 1 factorial f of n minus a h plus h n by n factorial a, which is equal to f of a plus h. So this let us take as equation 2. Now we are going to differentiate this equation 1. This function phi x we are going to differentiate. So if we differentiate this function here, so we are going to differentiate this function. Here it's already taken here. So we are going to differentiate this function. So if we differentiate this phi x here, okay, so phi dash x we are going to find. So if we differentiate fx, we get nothing but f dash x. So I'm writing here f dash x. But here we have, in this case, we have two functions, a plus h minus x is one function, and this is another function, f dash x. So we have to apply quick product rule of differentiation here. So if we use this, so I'll differentiate first this and leave this, I'll differentiate this first, then leave this function, then give plus sign, and differentiate, leave this function and differentiate this function. So if I do in that way, I'm getting here a plus h minus x. Since I'm differentiating f dash x here, it will be nothing but f double dash x. Okay, so if I differentiate this function here, a is a constant, we get 0, h is also a constant, we get 0, and if I differentiate minus x, I get nothing but minus 1. So we get minus 1 f dash x. So in the similar way, we have here plus, okay, plus a plus h minus x whole thing squared by 2 factorial. You differentiate f double dash, so we get f triple dash x. Now we are going to differentiate this. So if we differentiate this, we get 2a plus h minus x. Again, we have to differentiate inside 1, so we get nothing but minus 1. So we have here minus 1 by 2 factorial f double dash x. So in the similar manner, we are going to differentiate this. So when we differentiate this, after differentiating, we can check there that this will be cancelled with this, and this will be cancelled with this will be cancelled with this, and this one will be cancelled with someone here. In the similar manner, everything will be cancelled, and we are left with only this and this function. So we'll try to take common from here, whatever is common. So if we take common here, we get this to be, we're getting here as a plus h minus x to the power n minus 1 divided by n minus 1 factorial fn x minus a. That we let us take this equation as equation 3. Now here we can see here, if we had, since we had defined phi x as fx, and we know this is also continuous, so this is continuous, so product of two continuous function is continuous. Similar way, this 2 is also continuous, this is also continuous, and this is also continuous. So the sum of continuous function is continuous in the closed interval. So that is the reason why phi of x is also continuous in the closed interval a to a plus h. So here we get phi of x is continuous in a to a plus h, and also we have here phi of x is differentiable in a to, in open interval a to a plus h, and phi of a is equal to phi of a plus h we have choose already when we take a. So we have these three conditions shows that it satisfies all the condition of Rolle's theorem. So by Rolle's theorem, we can say that there exists, okay, we can always find one number lying between a and a plus h such that a phi dash of that will be equal to 0. So here I'm taking phi dash of a plus theta h is equal to 0, where 0 is less than theta is less than 1. So I'll substitute in place of x here a plus theta h. So in that way here also you put, so this is in product, so this will go this side, so it will become 0. So we are left with this. So we have fn a plus the h minus a, which is equal to 0. From there you can find a, so we have a equal to fn a plus theta h. So this we take as equation 4. So you put this value of a in equation 1. So we are trying to put the value of, sorry, not in equation 1, we'll try to put the value of a in equation 2. So you put the value of a in equation 2. So if you put the value of a in equation 2, we get here f of a plus h, which is equal to f of a plus h f dash a plus h squared by 2 factorial f double dash a plus hn minus 1 by n minus 1 factorial f of n minus 1 a plus hn by n factorial fn a plus theta h by using equation 4. Okay, where 0 is less than theta is less than 1. So this is nothing but the Taylor's theorem. Thank you.